your index finger, the last 8.
Hey folks, thanks for tuning in this afternoon. No music quite yet, but I've got a little surprise for you, or a little experiment, I guess, so I hope you like this. That was me playing. I should have had myself on the camera so you could see what it was, but I was there playing for you. We'll do it again at the end, maybe. I don't have a camera at the front of me when I'm playing marimba, so it looks a bit weird if you could see the back of me. It's the last lecture for COMP2300. What a time to be alive, the end of the course, week 12. I think, oh, I'm missing some of my lights. I think, you know, when we started this whole shenanigans online, people wondered how this would work out, and I think that most people have had a pretty okay time. Definitely been okay. Definitely been okay doing the lectures and getting some great questions here on Teams. I know some of the online labs have been really tough, but I think you'll agree that the tutors have really put in a fantastic effort to make sure that they're engaging with all of you folks out there. So if you haven't yet, this week would be a good time to thank your tutor on Teams. Just drop them a line and say thank you for spending a lot of effort, because I know that some of them have worked incredibly hard this semester to help you folks out. And I'll thank the tutors as well. So we're here in the very last lecture, and this week was all dedicated to revision. Now I know a lot of you will be quite focused on getting your assignments done, not just for COMP2300, but for all of your other subjects, because I'm sure you've got a million assignments to finish up this week. As we went through on Tuesday, we had this big focus on trying to get a high-level overview of all the topics in this course. So I'm just going to get to where we got up to. So I've got that diagram again. The next one. We did functions. I just want to go to the last time that we had the diagram. Here's the diagram. So this is all of the topics from this course. I've got the wrong mouse in the wrong spot. Here we go. All the topics of the course. Now, on Tuesday, we talked about digital logic, went through our digital logic checklist again. We had a good bit of work on the hardware-software interface. So just to remind you, a hardware-software interface is all about how you connect your sort of software programming to the CPU hardware. And how do we do that? Like, it's with instructions. And instructions that let us operate on all of the CPU bits and pieces, right? Address the ALU, putting numbers into registers, accessing the memory. All these instructions, which you know from your cheat sheet, are part of the hardware-software interface for your disco board. So that's a really, really important topic. Then we got started with this sort of, well, this bubble is kind of the world of computing instructions, where we started out with this course, learning what makes a CPU tick at this very basic and low level. And we also touched a little bit on architecture, right? Because we looked at the basic CPU model. I'm just going to make myself small so I'm not in the way of the diagram, or maybe left-hand side, how about that? Then we moved on to this other bubble here, high-level thinking to assembly. So really, the concept of this bubble is, now that you know about assembly instructions, you know how software can talk to the CPU, now we need to know how to go from the high level of abstraction when you're coding in a language like Java or C or Python, and how do you translate that kind of programmatic thinking, algorithmic thinking, into assembly programs that you can run directly on the CPU. And this stuff was really, really important for actually getting work done on your disco boards. And remember, if you cast your minds back to like lab 3, where you really didn't know how to do anything and you were just learning about how to do a little bit of maths, just adding a couple of numbers together on your disco board, and then learning a little bit about conditional branching. So going to one bit of your program when if a number is higher than 10 or something, and then going to another one. Then we started to learn how to do this a bit more formally from a functional point of view, talking about functions there and back again. And then today we're going to start off with control structures. So how do you take the for loops, while loops, if then else blocks that you find in all programming languages or generally in your everyday programming languages, and then how do you turn that into assembly instructions so that you can get work done. I know you can all get work done now because I've seen your assignments, and you wouldn't be able to do those assignments and labs unless you could start to think in assembly programming levels about how to do control structures, how to do data structures, and how to do functions. So that was an incredibly important topic for the learning outcomes of this course. Now we'll finish up today with this third bubble. So it's kind of like from your disco board to the world, right? How does your disco board connect with other devices? How does it conceptually connect with bigger computers like laptops, phones, embedded devices? How do you do bigger software like operating systems? And then finally, we kind of come back to architecture, which is kind of where we started. So we travel full circle in this course, back to architecture, and look a bit at how CPU architectures work in the real world, looking at some different examples, and in particular, looking at a few concepts to do with multiprocessing. How do you fit copies of various parts of your CPU onto one single processor in order to run programs faster, run multiple programs at once, run an operating system that's multitasking, etc. So this was out of these ones, this was the real topic which had kind of really clear connections to assembly programming. This one was more to do with some terminology and foundational knowledge. This one was to do with terminology and foundational knowledge and connecting up with the idea of context switching. And then this one was kind of a real quick tour through basic ideas about CPU construction. So these ones are all kind of the foundation for you to then go do other courses and learn more about them. And in particular, this one, right, you've got a whole course coming up to do with that. Actually, this one, parallelism as well, or distributed computing as well. So those of you doing COMP2300 will be doing a whole lot more concurrency next semester. So this is a great one to get your foundational knowledge sorted out now in this course, do your study now. Then when you get to the first lecture of 2310, things will make sense. If you don't have that foundational knowledge now, it will be much trickier to get started in 2310. Now, let's get started with control structures. I'm just going to flick through functions, main topics, store and pop onto the stack, passing by copyright reference, function stack frame, recursive function, talked about that on Tuesday. Here we are at control structures. So the main topics of control structures, in short, conditional branching, which is sort of already done in the hardware-software interface, but now we have to look at it again, a little bit of a revision. Then doing the control structures in assembly code. The typical ones are the if-then blocks, while loops, and for loops. So here was your program status register. That should be XPSR actually. CPSR is old terminology. Here's your CPSR table for how you get the different condition codes and what they mean in English and what they mean in terms of how your processor tests them. So just as revision, this should be very much knowledge that you're in command of, but you would do something like compare R0, 5, that's going to calculate R0 minus 5 in the background, throw away the result and just set the flags. So if it turns out that R0 and 5 are equal, then the 0 flag will be set, right? So then we know that they're equal. If it turns out that they're not equal, the 0 flag won't be set. Yeah? If it turns out that it's less than or equal to, then we'll either have the 0 flag equal to 1 or the negative flag not equal to the overflow flag. So things get a bit tricky with when you're thinking about numbers that are like all the way around the edge of our circle of 2's complement calculations. So having a good, you probably have a good intuitive idea of how to use these ones, right? Whoop. Probably have a good intuitive idea of how to use these ones, and they're the main ones that you would use. These ones in the middle here you might not quite be so familiar with, so I would advise you to do a little bit of revision and try to work out a use case where you could use one of these ones, right? I mean, plus positive and minus negative is fairly obvious. If you end up with a negative result in a negative flag, then you would use that condition code. Now, the other thing to remember here was, that you could only use these with regular branch, right? BEQ, BNE, BGT, ELE. And typically when you were using these, you could only use them with the regular branch. And if you wanted to use them, for instance, with branch and link, then you would have to put it in an IT block, which would do a little bit of magic on your CPU to kind of extend its capability and let you do a couple more instructions. So I showed you how to do that in the control structures lecture. It was a little bit of extension knowledge, so it's not the kind of thing I'd be focused on, but I know people have been using it in assignments and in labs. I know it's the kind of thing that when you use it, you feel like, I'm a real hacker now. I know how to use these assembly instructions. So, feel free to go ahead and use them. But if you are using them, make sure you know what you're doing, because I do remember that I marked a couple of responses in the mid-semester exam where someone had thought, I'm going to use IT blocks, and then it would just gone completely off the rails. So maybe be conservative. If you know that, if you're not quite sure what you're doing with these, maybe it's best not to go there. Now, this is just a little bit of an overview of how we discuss these things all the way back in week 4. Week 4 wasn't, no, week 5. It was the first week we were on. I was here at home lecturing to you. And we did these, oh no, week 4, week 5? No, one of those. Anyway. We went through a couple of slides. We did this little pattern where we looked at all the while loops, all the if then else clauses, and all these for loops, and tried to find like the basic components, right? So in the while loop, for instance, you can see that we've got an expression here, something which is going to be either true or false, because it has a Boolean operator in it. So in this one, it's while register 1 less than 100. That's either true or false. So we're going to have to find some way to translate this into assembly. Then we've got the code inside the loop. So this is like the main components of a while loop. An expression, a Boolean condition, and the code inside the loop. And remember with while loops that the way it works is first we check the expression, and then 2, run the loop. Right? And if it's the other way around, then it's a do while loop. You do the expression first, and then you do the checking of the expression. So then it goes back to the top. So if you're implementing one of these, make sure you're very careful about the order that things happen. Because again, I see people giving responses in exams where, there's all these things are there, but they're somehow not quite in the right order. So in the best case, it's confusing. And in the worst case, you actually end up with the wrong answer than the while loop that they were going for. So then we had this little control structures gallery. This was the most important slide in the control structures lectures, where we looked at some very, very simple ways of kind of expressing a couple of different control structures. Looked at if then else, looked at a while loop example, and looked at a for loop example, right? While loop example, where are we? Oh, this is a bit tricky, isn't it? This is an Uwe slide where he's done quite a kind of enhanced version of it. So the first thing we do is we branch down to the condition checking. Then we do compare R1 with 100 to see if it's less than, R1 less than 100. If it is less than, we do the while loop. Then we do the body. The body's in that part of this little expression here. And then we go straight down to the second part of the expression. I suppose in my view, this one, it is a while loop, you're doing the same work, but it's not quite clear in the code what is going on, although the answer is definitely going to be right. And then if we fail the while condition, we just drop through to the next code. For the if one, we're going to do the check, compare R1, R2. Then if they happen to be equal, we do the go down here to the then. Then we've got the else here, and then this is the sort of escaping our loop. So the trick with this structure for the if then else, if you remember, was that we don't start with the then. This is the else bit. Else is here. Else move R3 0. So it's if else then, actually, when we do it in assembly. Well, you can do if then else if you want to, but if you do if else then it saves a step of having to branch somewhere else. So you save some instructions. And then for the for loop, first thing we have to do is set up our for loop counter for R1 starting at 1, going up to 100. So we set up our counter there. Then we compare R1 with 100. If it's greater than 100, we exit the loop. And if it's not greater than 100, we do our loop body. There's the body. And then we do our increment. Incrementing things is a very common operation. And in ARM, like to do an increment, you have to do this, add with an immediate add, a good way to do an increment. In other architectures, for instance in x86, I think there's an inc operation where you can increment a register or a memory location without having to put the immediate in. So such a common operation that it got its own instruction. And then once you get to have finished the increment, then you go back to the top of the loop, the for bit, and then do your compare. So these ones are important. Make sure it's the kind of thing you practice and get right after trying many attempts. I think for those of you who have been using kind of, and I know many of you are, using kind of a good balance between high and low level thinking in your assignments, thinking about ways to make things modular, and thinking about ways to create assignments or to create code in your assignments which could do more than what you have commanded it to do. So you're being modular about it, making it easy to extend. You'll end up using a lot of these concepts because you'll be thinking about high-level programming. And if you're not thinking about how you might do a for loop or a while loop in your assignment work, well, there's still time. Where might you want to use these loops in your assignment 3? Good question. I'm not even sure. So, I just asked you this question, didn't I? I guess, something you can consider now is whether there were things in assembly that go beyond typical control structures. So are there other control structures that are possible, which we don't have in the normal ones that come with C or Java or Python? What else might you be able to do? Maybe it's a good time for have a little chat in in the comments. So I'll just ask you that question. Other kinds of control structures do you think be possible in assembly? Sip my water. Adam's already had a response. Now you can do a lot of ad hoc looping. Yeah, what do you mean by that? Find a nice synth to play along while you're thinking of some answers. Oh, a switch statement. Yeah, a switch statement is a good one. One of the wild things about the switch statements is you can in assembly do actually like the lowest level version of a switch statement, which is to like make a vector of different actions, and you can implement your switch statement by implementing offset branches into some kind of vector of other memory locations. Oh, so I can't seem to. I want to not be in full screen. Exit full screen. Go there. Go here. Okay. Yeah. Where's my classist? Any more thoughts? Yeah, so Isabel's saying that some objects in Java are iterable, but in assembly, like anything you make could be iterable, which is kind of an interesting way to think about it, right? In higher level languages, you rely on there being some kind of structures available for you to operate in, but in assembly, you're free to make your own structures. Any other thoughts? No? Oh, new messages. Gabe has a great idea here. Switch could be implemented by storing the label value in an array, but that would likely be error prone. Oh, now I want to show you another slide from last year. Let me see if I can find where it is. COPE 2019 full. Oh, I might have to email it to myself or something crazy. Yeah, I guess what I'm trying to say is that like that method of storing label values in an array or storing actual locations in code is exactly how like a switch table should work. That's the implementation. You have an array in memory of program locations, just like your vector your interrupt vector is a table in memory of memory locations, and then it switches through that by just counting through up to the number of interrupts that has been triggered and getting to that integer. So in the same way, you can do a switch in assembly by storing in memory an array of program locations. Your code says, I've got a 5, I just have to count down to the 5th location in the array and branch to that address. And that's your very efficient switch statement. Yeah, let's move on. Oh, I forgot to record. Duh. I'll have to download it from YouTube now. Yeah, Adam has said now, in order to actually compile things, all of the control structures in high-level languages should be possible in assembly. But of course in assembly you can, I guess my point is you can kind of invent your own as you go. You know, this is another point of kind of classic exam question. You've already experienced a few of these. Making up a loop or an if-then-else block in Python or Java. Try something where you just make up a few and see how quickly you can translate it into ARM assembly. And I want you to focus particularly on how you know that your answer is correct, right? Are you going to have to do some tests with it? Do you have to compile in your head? How are you going to run through that code and make sure that you've written down the correct answer and not something which is going to give me the wrong result? Yeah, so on to our next topic. I think we've got there's a bit more discussion going on about vector tables in the chat. I was just saying here, well, you'd use labels, and then the assembler would look after the addresses. So the data structures week. Data structures. We were looking through these topics: arrays. Then we looked at structure of arrays in memory, how they might be aligned, how they might be addressed, how you iterate over them, and how you might copy them. And then we did records, which is somehow not in this list. Anyway, we'll get to that in a minute. So this was our typical array in memory. You've got, you can see now we're at the bottom of our user accessible memory, going up and up and up. See what Callum has to say here. Oh, great. He's got a really exciting... Let's open this on Stack Overflow. I hope it's not going to like rickroll me or something. Okay. Ooh. Work out a simple table branch byte in ARM Thumb. That's pretty cool. How is that actually an instruction? I forgot. TBB instruction. Yeah. Derp. This is in the this is in our version of ARM. Someone tell me. I forgot about that. Great point, Callum. Okay, so we've got our array in memory, and of course, in this case, we're doing an array of word-sized objects. So all of these objects are going to be 32 bits. So they're going to take up 4 memory addresses for each one, because as you know, each memory address on our disco board is 1 byte of memory. It's byte address memory. So the first array index will be the address of the lowest location there. And this one will be the address of that lowest location. This one will be that one. That one. So a few questions. How do we know how big an array is in memory? Is it possible to write outside the bounds of an array? Can you make an array where the size can be changed, a mutable array? And how might we address a particular element in the array? So maybe we'll just think about the, thanks Benjamin for informing me, keeping me on my toes here. So some questions. How do we know how big an array is in memory? Yes, it's like I've put a question on Piazza and And Mitchell has just addressed me in the manual. Page 462, didn't you memorize that one already, Charles? Oh, sorry, guys. I didn't memorize page 462 yet. Can you make an array where the size can be changed? Yep, Robert MacArthur's got some good ideas here for an array where you might be able to find out how big it is in memory. So if you know that the last element of your array is a 0, then maybe you could go through each element of the array, traverse the whole array, counting all the way up to that until you find the 0. So if you had a string, an array of bytes in memory where the last byte was 0, you know it's a 0 terminated string, then you can count up to that and you'll have the size of your array. And then the other option was like defining an array with the size at the top. So, or at the bottom might be a good idea. So the very first thing you find is its size. So you don't need to do the whole traverse. It'd actually be faster to look up its size that way. Yeah. So what might be the, I guess you would trade off memory size for a bit of speed if you just store the length, right? Yeah, I think Adam Rowland's got a slightly different interpretation here. How do you know how big an array is in memory? We don't. How are we gonna know that? This array is just a bunch in my version of the slides. This array was just a bunch of memory, and then what came after it wasn't anything except more memory. There was no 0 at the end. We hadn't stored how big it was. So I happen to know, because I wrote the array, that we've got 8 elements here, but there's no way to find out if you don't know that. So we must be careful with arrays. And I think this is the kind of thing which, you know, made a difference in assignment 2, right? When you had to implement an array in memory to store a song, and sometimes there was code where a sequencer could play an array, but it was hard-coded into it that that array would have exactly this many elements. And when you got to that many elements, which you knew beforehand, you could loop the array around. And maybe a more sophisticated way to do that would be to have some method so that your code can find out how big the array is. Why would that be better? Well, maybe someone might want to go into your code and change the array of notes and durations in order to put a different song in there. And if they have to change that in 2 places, somewhere else in your code has to change this hard-coded a length number, then it's not very modular, right? It might even be that someone wants to extend your program to load arrays from disk elsewhere or out off a network or somewhere. So in that case, it would have to find some way to calculate for itself how long an array is. So these are good. I put these talk slides up because they're kind of like, you know, the kind of exam questions I ask you. We've done them in the mid-semester exam. A lot of them are going to be these quite hypothetical questions where many answers could be correct, but what I'm looking for is some justification and following through this thought process and make sure that you understand how arrays really work. Array addressing. This is another UVA slide that I borrowed. So we could see in this version, Uva is starting from the top and going down. So X would be the starting point of the array, and ES would stand for element size. And in this case, the element size is 4 bytes, but we don't know how long it is. Then the address of the first element in the array would be X base address plus 0 times ES. So it would be X plus 0 if we're using 4-byte addressing. Then the next one would be X plus 1 times ES, and so on. So you've got your element size and your array addresses. And we did this in the lecture. I did little array examples with you, working with the element size and the indices. Here's a fun one. What's the ending memory address, the last memory address that's part of the array? So this is the last element, but the last memory address that's part of the array is x plus 4.es, which would be an element starting here, right? A new one, E4. But where this one doesn't exist, so we just go back 1 byte to get to this, the very last address in the array. Uva's slides from last year have a lot of good questions in these little boxes. So can arrays always be stored packed? Well, this is it's handy in this case that our elements are all 4 bytes. So they're kind of neat offsets. But if you had an element which was 3 bytes, then you might get into trouble in terms of your addressing, because you'd end up with 3-byte things that are not on a 4-byte boundary. And actually, sometimes when you do a read from memory which is not on a 4-byte boundary, it takes a lot more time because the architectures could have behind the scenes some limitations about how they can read words off memory. They can read words on these 4-byte boundaries, but not on any old place. Of course, if you ask it to, it will do it, but it does it by spending more time on it, doing it in the background, and then giving you the result as if it never had a problem. So it's kind of cheeky like that. And I like this down here. Again, what we're telling you to do, you're an assembly programmer. You have absolute power over your computer. So what happens if array bounds are violated in this case? If you start writing to extra places outside of your array, who's going to stop you? Nobody. So who is checking what the array bounds are? You are. You're the assembly programmer. You are in charge. You are the dictator of your little computer. You don't have an operating system or a runtime environment looking over your shoulder saying, wait a minute, that memory has been dedicated to someone else. That's protected memory. You can't write there. Nope, it's all up to you. Here's a little example adding up the numbers in an array. We did these a million times. I'm not going to go through them in particular, but here's where we've sort of stored how many numbers are going to be added up. 0 to 7, our base address. We're setting ourselves up by getting some register to store the result, which we'll call R3, and another one to store the register size, which is going to be 4. I'm going to get to Isabel's thought in a question, Isabel's question in a minute. Our array sum procedure here is going to have this calculation of the offset, right? Element size times index. Put it into R5 to store it. Then we're going to load R0, the base address, offset by R5. So we're going to do an offset load to traverse through the array. I asked you about that in the mid-semester exam, if you recall. Then we're going to go load that data into R6, add R6 into our accumulator. Then we'll increment our index, compare our index to R2, the top index of the array, and go back to the array sum loop. So what kind of loop is this? So Isabel's question is, on the topic of what we can do in assembly that isn't possible in higher level languages, you could have an array where each element is more than 1 byte, and if you want to read byte 2 of element 4, In the high-level language, you probably have to read all of element 4 from memory and then get byte 2. So in assembly, you could just compute the address for that 1 byte and then only read that byte. So really good point, Isabel. Because you have control over memory, you can do more precise loading and storing to memory than you generally do in a high-level language. In the high-level language, you have to deal with types, right? And if you knew that some element had 4 bytes, that's not going to help you much. You have to get that whole element, sort of maybe cast it as a different type, turn it into bytes, like taking a string and turning it into bytes in Python, then access that element of it and extract it out. Yep, Adam's got the right of it here. Looks like a do-while loop. Looks like a do-while loop to me too. Official COMP2300 thumbs up for that one. Okay, what about records? So we had arrays, which are like when you've got a bunch of really neatly ordered things, all in memory, all perfectly regimented, all the boundaries are the same, and your records is just a whole bundle of different information. Now, it's a whole bundle of different information, but it's a whole bundle of different information in a specific order that you set and you have to remember when you're accessing your record. So we could do this with kind of a little example from Hearth Pebble. If you wanted to store your character's HP, mana, and name, we could have 2 words, but one storing HP, one storing mana. That would be the first 2 elements of your array, of your record, sorry. And then after that, there could be a 16-byte string for your character's name. So that would be your way of packing in some data about your Hearth Pebble character. And I think I showed you in that lecture, if we make a little function to access locations in that record, you can reuse that function for any record as long as you have its base address. And then I think I pointed out that in C there's something often called a struct as well, similar way of doing this. So some people would call it a struct. I probably would call it a struct on any day of the year, except when I'm teaching COMP2300, where I specifically use the word record. So just make sure you translate it in your head if you understand the other version better. Now we also can use this for things like synthesizer commands, right? You could have a record, a record where all of your instructions for doing one note are stored, like its frequency, phase, amplitude, and the type of waveform to use. Could be one way of storing things. It's the kind of thing you could do in a sequencer, but wouldn't be not specifically used in this course, I guess, unless someone wanted to do it in the assignment. Yeah, Gabe is saying close to a 4, I think, is there's a counter that directly governs the number of iterations. And then Adam says, well, a for loops typically have the check at the start of the loop. Exactly, that's a for loop. The check is at the start. And this one, the check is at the end. So you're doing it and then doing the check after. So, you know, really important to think deeply about what the kind of expectations are behind for loops, while loops, do while loops, and your other program constructs that you use every day. I know it doesn't seem like it makes much difference, but it's important, right? Where exactly are certain operations going to happen? So this would be a for loop. For this to be a for loop, the first check would have to be not assumed. But because it's a do while loop, the first check is assumed. Well, the first check doesn't happen. Check's after. Okay, what's the difference between an array and a record? A very good question. I just told you the answer. You can have a think about it and get back to me on that one. That's another point that we've really hammered home today. Now here might be a good, exam style question. I might put this in practice quiz on Waddle for you, which I haven't quite finished yet, so you'll just have to bear with me on that one. I'll get that out to you soon, but you've got an assignment to do, so give me a break. I'm giving myself a break, I suppose. Imagine you're creating a point of sale system, so like some kind of cash register using a disco board. So what data structures might be required for your point of sale system? I'm going to put this question in the chat and see if anyone has any thoughts about it while I'm continuing to talk. Oh yeah, and then we go to our other topics. So we've done this kind of high level thinking to assembly zone now. This is all done. Tick, 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 tick. And that took us a long time in this course, up to the end of week 7 to get that done. 2/3 of the course was these topics. Yeah, so Gabe has started to brainstorm a couple of really important data structures that you could use in your point of sale system, or important bits of data you would have to imagine. You know, making a little design like that is, and thinking it through, thinking what memory structures would be required, is the kind of thing that we've been training you to do in this course all along, right? In your 3 assignments, we asked you to design something, explain what it is, explain how you do it, and just make a discussion about why those things are appropriate. So these kind of questions are really where we've been focusing your training. Isabel's saying a record data structure could be each transaction, probably need an array of records to record a sequence of transactions. And then how about storing like stock levels, etc. Now we're going to go on to our next area, asynchronism, interrupts, and concurrency. So I think, you know, this is where we really got to stretch out our understanding of how your hardware software interface works, because for the first time we considered things happening which were out of your control, an interrupt. Why is that important? Well, so far, up until that lecture, up until week 8, every time you wrote a program, you knew which was the next program counter location which would go at any one time, right? It might have been complicated, but you knew what it was going to be. Whether it was moving through a waveform, going up and down for a triangle wave, whether it was counting through a song, whether it was playing a game of Hearth Pebble, you knew what the outcome was going to be before anyone else did. Then when we got to this one, there was going to be code running at times where you don't control it. And that was what made it so exciting and really changed the game in terms of your mental model of how programs work. And this might have been the first time it happens in your programming experience that you don't know exactly what happens next in your program, because you always have to think when you've got interrupts available, is this next line of code going to run, or is it going to be put to sleep and my interrupt handler code is running? And the reality is you won't know, particularly if you've got your interrupts connected by a hardware wire to some other system that could change the voltage anytime, or have a button where the user presses it and does something. So it was a bit wild. We talked about when and why interrupts and or exceptions, the other name for them, would happen. We talked about the process of what happens during an interrupt. We discussed how this is related to parallel computing, which was really about focusing on how to do a context switch, how to switch between 2 programs at once and make sure that neither of them knows what the other is doing. Then in our concurrency section, we talked a bit about race conditions. Remember, just jog your memory for a minute on the too much milk problem. And we discussed the solution for that problem, which was developing a higher level concept called a mutual exclusion, some way to prevent a race condition from occurring. Then we had the two versions of that. There was one which was like the very simple lock-free mutex, then a lock variable and semaphores. We had practiced implementing those in assembly too. So you have to remember when we do our interrupts that it involved a hardware alteration to our computer. It needed to be hardware supported. So put some wire into the sequencer that can stop the process of updating the program counter to the very next location. It can stop branching to a particular location. do something to save all of the current context and then put some other program counter location in there and direct your CPU towards doing the interrupt handler. And we have to remember that this is absolutely necessary. You need to do interrupts all the time. If you want a keyboard to work, you need interrupts. If you want a mouse to work, you need interrupts. If you want a synthesizer to work, you need interrupts too. You're not going to be able to make a computer system with our normal computers unless you have a very specific hardware scenario where interrupts are not required. And now you've been doing assignment 3, you know all about interrupt controllers, right? You understand the complexities of the nested vector interrupt controller and the external interrupt controller on your disco board. So what happened when you ran an interrupt? You guys all know this now as you're deep into assignment 3, but your interrupt handler would be a normal function. That's the way it's designed in ARM, which is called when an interrupt is triggered. So the CPU has the job of saving the caller save context onto the stack and then loading up LR with a special value. And the special value means rather than returning to some place in memory, you're going to untangle that context off the stack first and then go back to where the program had left off. So the stack, our program might have been running like this. We had a normal couple of stack frames, that's like function 1 and function 2. And then here's the interrupt in the stack history. And then we end up saving the state of our computer. That was the caller save context, was saved by the CPU. And then the interrupt handler, just being a normal function as it is, has the responsibility of saving callee save variables onto the stack as well. Then your handler does its work, BXLRs out of itself. The special LR value goes into the sequencer, the CPU knows what to do and puts all this stuff back into the CPU, and our code starts again from there. Fun times with interrupts. Any more questions? Just going to check the question levels. Determinism is so boring, says Adam. I agree. Now the connection between interrupts and like multiprocessing or parallel computing was this idea that we could use interrupts to run two programs simultaneously or trick their CPU, trick both programs into thinking that they're running at the same time as the other. So the way we did that is once the interrupt controller in this version has put this code to sleep, and it's running in the handler, then the handler itself can be actually, instead of taking us back to this program, can switch around the stack. All it needs to do is change SP to be SP2, have another stack, and it can in fact wake up a different program. So in this example, our interrupt handler, we now call a dispatcher, that's the handler. This program was running over here, it has its code and it has a stack. The interrupt handler saved all that stuff on its stack, did some callee save variables if it needs to, and then it takes the stack pointer here and stores that in somewhere else in memory to keep it safe in a process control block. And now that we've done the operating systems week, you understand more about how to conceptualize a process and what information would need to be stored about a process. So now this whole process is asleep. Zzz. In this side, the handler takes the SP from this program, puts it back into the stack pointer location in memory, right? Now that SP goes into R13, that's the stack pointer, isn't it? And then the handler BXLRs out of that, and our program counter ends up back in our regular code. So this program is waking up now. Wake up. Is that clear? It's a complex process. Maybe it's best to, if you're not quite sure on that one, jump back to that other lecture on context switching and interrupts and asynchronism, and make sure that you have these concepts clear. So here's like a couple of general questions, exam style questions. What problems can occur when running concurrent programs, and what are the possible solutions? We're going to talk about that in a minute because we're talking about concurrency. But what I wanted to draw your attention to is thinking about how this very simple example of the too much milk problem can help us understand this issue. So if you don't remember, the too much milk problem goes like this, right? There's two roommates in an apartment, okay? Could be at uni lodge, two roommates, one apartment. And there's one fridge in the apartment. So both of those roommates are out at uni during the day. They're studying in the Chifley Library because there's nowhere else to go at uni campus right now. One of them gets home, opens the fridge, there's no milk in it, and closes the fridge and goes out to go grab some milk from the shops. The other roommate now comes home, opens the fridge, no milk in it, they go to a different shop. Now, the first roommate now comes back, puts the milk in the fridge, and is happy, continues their afternoon. Now the second roommate comes home, opens the fridge, and there's now too much milk in the fridge. They've got two milk jugs, and one of the milks, can't go anywhere and has to be thrown on the floor. So obviously we have to have some solution to this. I think great concepts, Isabel. It's the one option was that the first person who's opened the fridge, maybe they could put a padlock on the fridge to stop someone else getting in there. Maybe they could put a note on the fridge to remind someone that they don't have to check the fridge right now. Tell them what they're doing. Or they could have some method of recognizing when the fridge has been opened in the meantime, and if it has been opened, they might have to check again whether there's milk and return the milk back to the supermarket. I'm not sure that milk returns are available at supermarkets, but they could be. Yeah, so Isabel's raised a really important point here, which is that because you're doing assignment 3 with interrupts, you're practicing this a lot, it just demystifies what's going on. Yep, that's the course design, right? You're not supposed to learn things just by having me yell it at you for half an hour. You practice it, you study it, you internalize it, and then the concepts all fit into place. And something like interrupts is a bit of a weird concept, particularly dealing with the priorities. So I'm glad that you're getting the handle of it now. So when we had the too much milk problem, what we ended up with was some kind of race condition where two threads of execution were happening more or less simultaneously. Two people in the apartment both going shopping, and we don't know what the result is going to be. Is the first one going to get back first? Is the second one going to get back first? Is the first one going to return before the second one even arrives home to check the fridge? So we don't know what the outcome will be. That's a race condition. And the bad outcome is that both people end up getting milk and milk is spilled on the floor, which we don't want to do, although we don't want to cry about it either. That would be a waste of time. So when you're dealing with these kind of race conditions, these things happen in your computer when you have two threads of execution which are accessing a shared resource. And in the case of the milk problem, they're accessing one fridge. But on our disco boards, we could think about that as accessing a location in memory that both people want to look at. So we have this concept of a critical section, right, highlighted here, where both threads are looking at the critical section. And obviously, the issue with this example was working out what the value in the count would be in each thread, because each thread is updating this location in R4, loading it up, adding one, storing it, loading it up, adding one, storing it. So there's lots of options for what could end up happening in that variable as we're trying to count it up from 1 to 100. So this was the basic solution, right? Our critical section, 2 bits of code trying to access the same shared resource or location in memory. First things first, we have to do some kind of negotiation maybe to work out who goes first. Maybe whoever gets there first just goes for it, and we ask for permission, we ask for forgiveness, not permission, or maybe they have to check some variable to work out, am I allowed to go now? And then at the end of the critical section, we indicate that it's been completed. And in ARM v7m, we have the literex instruction, which we can use to do a kind of lock-free solution for this. The way this works is that it has a bit in memory which is set to be like, I have exclusive access to this memory address, to a memory address, one sort of exclusive store, one bit in memory. Then we do our work, and then when we're storing back, we look back at the bit and see if it's still set. And the trick with that is that if, in order to run this code over here, we have to have a context switch. And that means we have to have an interrupt. And that means that our exclusive store is cleared. So they'll be cleared when we go over here, and it'll be cleared when we come back. So if there's been a context switch in between here and here, then our exclusive store bit will be 0. And then we'll go look at it. The store won't succeed. StoreX only works if the stored bit is still set. So then StoreX stores a 1 in a value to make sure that we know that our store has failed. And then if that's the case, we have to then go back and try it again. So that's our lock-free method. Other two methods which we went through, I'll let you revise these on your own, but first one was to have a lock variable, which we would set up. And this was good because it means that our work for setting the lock variable can be short or a controlled length of time, and then we can spend a bit more time in the critical section without worrying that we might be interrupted. The other thread will leave us alone. So this can be short and this can be longer. In the other hand, this can only store one, either a 1 or a 0. So in this case, 0 means unlocked. If we had a resource where we could actually have multiple people using it, maybe we had 3 printers and there were 3 threads that could use them at a time. That seems a bit of a weird example, but okay, 3 printers or 3 GPUs and 3 different machine learning programs can use them at a time, but we have 5 running, so we might want to count to a higher number than 1. In that case, we can use semaphores, which have a generalization of the lock to allow more than one thread to access this shared resource at a time. So only with a few more lines of code, you can implement a simple kind of metaphor. I'll let you revise that one. Networks topic. I want to keep moving in this lecture so I get through it all. Networks main topics. This was a big information dump that week of lectures. It was all about terminology and kind of structures that are used to work out networking protocols in the world, and then we kind of use only a very limited amount of it in our actual assignments on networks, which you're doing. But the topics were the mediums, communications protocols, packet switched versus circuit switched, simplex versus duplex, topologies, parallel versus serial, timing and synchronization, and that 7-layer OSI model. Whew. So these would be some fun questions you could consider. When we went through topologies, I think I only really talked about 3, which was bus topology. Every node on the network is connected to a line, single line, and each one would kind of receive every message. So if this one wanted to talk to that one, the message is going to go to everyone else on the network as well. And it's their responsibility to say, no, I'm not the one that needs this message. I'm not the one that needs it. I don't need it. I don't need it. I don't need it. Comes up to here. Yep, I need it. The ring topology, right? Every person is connected to 2 others in a ring. So if this person wants to talk to this person, they're going to have to send a message. And if a person gets the message, but it hasn't been addressed to them, they pass it along. Oh, it's addressed to me. I'll take that one. And in the star topology, then this person in the middle has the responsibility of sending a message to the right person. So if this person wants to talk over there, they're going to have to tell that person, I want to talk to this number 6, right? And then that person will send it the right way. That's this node is like a router. Another topology which you might have heard of is this fully connected topology. So every node is connected to every other node. And this means that each person in the network is going to have a lot of information about who all the other members are. And if they want to send a message to it, they can send it directly. That one's going to be really complicated. Oops, no. The mesh topology. How's the mesh topology work, James? Is that kind of like fully connected? I'll just look it up and remember. Mesh topology. Yeah, I mean, that's going to be kind of a mix between some fully connected ones or maybe some star ones and some others. So in the mesh topology, right, everyone's kind of self-organizing. Every node is independent. They're going to talk to who they can talk to. And if they need to send a message along, then they can work out amongst themselves what the addresses is going to be. Yep, each node's connected to multiple other nodes. Yeah, tree is also super common. I mean, I only had 3 topologies. Like, you can do a whole course in topologies in maths. It may be not what you want to know about networks, but tree topology. This is like the hierarchy. This was the Bell telephone system, right? Which we talked about on Piazza the other day. The fat tree, I don't know what a fat tree is. You'll have to tell me what it is, Callum. Sorry, there's people messaging me all over the place. No. I'm in a lecture right now. Please stop messaging me. I know. We'll do after. Yeah, we've got important stuff to talk about. Parallel topologies. Serial versus parallel. So we did our serial connections where data is sent 1 bit at a time, right? So you're going to have one line which is going to send some data up, down, up, down, up, down, up, down. All of the downs would be a 1 maybe, and all the downs would be a 0, all the ups would be a 1. So if you want to send a message, you have to time out this sequence of movements on that one line. In the parallel connection, maybe if you have 8 lines altogether, you can send a whole byte by just setting all of their voltages. So you could send a whole byte at once maybe, but you need to keep everything in sync, which is trickier. Simple one, serial tends to be the way to go, although in some senses if you're trying to conceptualize a design, doing the parallel one often seems like an easy option, right? If you've got one node connected to a bunch of sensors or actuators or something, you could have some parallel network topology going in all those different directions. And the problem is that if you end up having like 20 or 30 different connections, then you're going to run out of wires. For instance, on your disco board, if you want to have a lot of different connections, parallel won't work that easily after a certain point. Whereas if you've got serial, you only need the one wire, but then you actually have to do the work of designing some data protocol to send the information all around your network. So you'd have more stuff to design. synchronous versus asynchronous, well, that was about whether a serial connection was clocked in or not. So in this instance, synchronous version, a clock wire is running all the time, which is telling us on the upswings that it's time to read the data off that line. That's a very simple way to do things, but it needs two wires. You can actually just have a very simple one-wire connection where the trick there is that both the transmitter and receiver have to know how to count time accurately. So both ends have to be a bit more of an advanced computer. This one on the right can be very simple. And the OSI network layers. Oh, a lot of information in that one. Physical layer, data link layer, network layer, transport layer, session layer, presentation layer, application layer. Now, I guess one of the concepts with the OSI network layers is that if you're trying to get your application is trying to get a message all the way over here, conceptually you're supposed to be like adding a little bit of a wrapper around that each time. It's like you're delivering some food, right? Like if you get food delivered to your house, like from the supermarket, of course you don't just get a bag with a bunch of carrots in it. You probably have the carrot has been put into a bag by the carrot company with some other carrots. You've ordered a kilogram of carrots, and then that bag has been put into a plastic bag by the supermarket. Then all those plastic bags have been put into a big box in order to go to your location in the city on one truck. Then all those boxes are put into a truck, and that truck is going to go around to everyone in that location, unpack the boxes, and take the bags that belong to you. So all of these different wrappings are going around it, right? Each time we're adding a wrapper to have a kind of lower level of abstraction. The lowest level of abstraction is like just the physical layer. So it's as if, in this instance, I guess the analogy with the Woolworths delivery breaks down, but it's if like carrots were walking along the road to get to your house. Well, that's not how it works, right? There've got to be a lot of levels of abstraction wrapping up those carrots in order to get them to their location that they need to go before they can enter your fridge. This is a great thing to revise. Looking in Wikipedia, looking in the links I supplied in that lecture. There's a link to a textbook you can read from learning.o'reilly.com, accessible to all ANU students. A great textbook on computer organization, which has a great discussion of all the OSI layers. Isabel asked if we can have an asynchronous parallel connection. Yeah, I think so. So an asynchronous parallel connection is going to be this kind. Whoops. I mean, it's just going to be a little bit trickier because you have to have all these other wires at the same time. They typically aren't done that way, but you'd have to be careful on the transmitter and receiver ends that you can get all of the data off those lines fast enough before the next read event comes around. So it wouldn't be that much fun to get that working. Operating systems. Whew, we're almost there. Why do we need operating systems anyway? What is the actual point of operating systems? Can't you just code on your disco board and make programs work like that? It's a great question for you guys to have a discussion about. Why do we even need OSs anyway? What's the deal with operating systems? I could get into Seinfeld mode now. They're always taking up memory. They're always crashing. Why don't we just run a program straight on the computer? What's the problem with that? Because the people are fickle. I don't understand that as an answer, Gabe. Why do we even need operating systems anyway? I guess one answer is that you like to have, a menu to open all of your applications. But really we determined in the lecture on operating systems that there's a distinction between our applications and our user front end, user interface, and the operating system itself, which is kind of working at a deeper level, making sure that all of multiple programs can work on your computer simultaneously, so you have multitasking, making sure that programs are sort of provided with an easy environment to run in, a runtime environment, giving them access to the hardware components of your computer, so each program doesn't need to directly understand how to turn on an LED on the disco board. It can just call an LED system call. Yep, it would absolutely, instructing hardware in pure binary would be a nightmare. It totally would. Yeah, back in the day, that's how it all happened. So, so having software that would work on multiple computers, types of computers, just didn't happen. Right? If your software would only know how to access the hardware on a particular kind of computer, not just like an IBM computer, but this particular model of IBM mainframe, because it had these instructions. And if you wanted it to run on a different IBM mainframe, a different model, then that you would have to rewrite the program because the hardware implementation is different, or you'd have to have a different model of mainframe which maybe has a compatibility mode with an older model so it can run the same code. And also early home PCs. So what's an OS? We've got these two main roles, right? Virtual machine, resource manager. In the virtual machine side, it's doing virtual memory, giving you hardware abstractions, doing process management, doing inter-process communications, and doing sort of, in quotation marks, this friendly and safe environment for your computer to operate. On the resource manager side, it's coordinating access to all of your resources, making sure that processes are scheduled for running on CPUs at the correct times, at good times, so everyone is sharing that access to the CPU. Doing memory management, so we're not running out of memory. Dealing with disks and mass storage, communications networks, devices, things like GPUs, DSPs, peripherals, etc. All of this stuff has to be shared between all of your processors on the computer. And we had a bit of a definition of a kernel, right? What is a kernel? Well, it was that core part of the operating system that's always residing in memory. It's the main part of the operating system that's taking all these core roles. So it's the thin line between this rabble of programs and the hardware which on your computer which needs to be shared between everyone. And if the programs, this rabble, want access to memory, they have to ask the kernel. Whoops, not the kernel of the army, the kernel, corn kernel. And they have to do that through a system call. So they'll just have a system call, and then the kernel will look at that and then maybe give them some more memory. Then we had a few different structures for kernels. This idea of having little modules that could be replaced within a kernel. So you could have a device driver that potentially is added to a kernel to give it access to different hardware requirements. In a bit of a more wild idea for a kernel would be to have one that's really, really simple and very, very small, called a microkernel, where all of your services provided by the kernel are also running in user mode, their regular applications, and then your programs are sort of communicating with these other service applications which are going to do a lot of the jobs that a big kernel would normally do. So that's an interesting, different approach to running it, making an OS. So some big questions over here was, in the operating systems lecture was, well, why are kernels and user programs separate? Isn't a kernel just a program? And that's true. But as I think James was making this point in the chat just before, it's going to be really painful if all of your programs have to address hardware in the same way that a kernel does. So the kernel takes on this special role of being in charge of the hardware and then giving out access to all the applications. And the applications give up direct access to the hardware. In exchange, it's easier to write them. And also in exchange, you can have some assurance if you're authoring a program that other programs aren't going to completely mess you up. Because if another program writes in your memory, then you can't operate anymore. So the kernel is like making sure all the programs are playing nice with each other. And the programs themselves have less privileges enforced by the hardware, those hardware memory protection units, for instance, to make sure that the regular programs can't directly access memory if we're using virtual memory, or if they can directly access memory, they can only access a bit of it. We defined a process. We talked a little bit about this a minute ago, but this was like our process control block where we had a process ID, some saved state, like the SP would be an important thing, the location of that process's stack and heap where we're storing dynamic memory. Whether we need to run this process as soon as possible by a deadline or just whenever we have time, and then what its state is, whether it's sleeping currently, or awake, or ready, or blocked by some other, blocked maybe. So if a program was waiting for access to memory because some other program has put a mutex on something, then we might say that that process is blocked. And so there's all these bits of information that could be stored in a process control block, which are crucial for running multiple processes on a computer at once. And we talked a little bit about how we might do multiprocessing with now we have processors, right? We could have like specifically one core for each process, so that's easy. We never have to do scheduling that way. Or we could have multiple processors. Well, these are multiple threads within one process, for instance, working on one CPU. And this one is another process working on that CPU. So they're going to have to share their address space and they're going to have to share access to their CPU and be swapped in and out of a position where they're running using context switches. And then this is more like what we have on our normal like Core i7 or, you know, ARM A15 or something, A53, maybe like on a Raspberry Pi, multiple CPUs and multiple processors. So the scheduler now has to be clever and give access to multiple programs at once when they need it. And maybe it doesn't actually use all the cores at once because it might be save power to not have as many processes active as are needed. So any process can run on any core if all of those cores are the same. Okay, and our final topic, architecture. We're almost there. Main topics of architecture: the history of computing architectures, Harvard versus von Neumann, pipelines, which is pretty wild, out-of-order execution, vector and SIMD instructions, hyperthreading, multi-core computing, virtual memory a little bit, and then a bit of discussion about alternative strange architectures that might be possible. So we came full circle back to this original slide, the simple CPU. So all of these components that need to work together to make your CPU work. Some code management, decoder and sequencer, memory. This is kind of the control unit of your CPU, right? These two blocks work together. One is decoding what code instructions come out of memory, and one is making sure they're in the right order. So that's where we could do our out-of-order execution. The interrupts is wired in there to stop it if we need to go to an interrupt handler. Some registers, location to store flags, and then one or more ALUs, then another memory management block to get information in and out of memory. I think this was actually an exam question a few years ago. What are the main components of a CPU? What do they do? Are any components unnecessary? That's a good question. What might be unnecessary in this CPU? Is there anything you can see here which we could do without? I'll let you have a think about that one. The pipeline idea. So if we have all of these elements of the CPU that are independent, we might be able to actually run things simultaneously in different parts. We potentially could have something running in the ALU while something else, another instruction is being decoded, and then some other instruction is being fetched. And they could all happen simultaneously, because if those parts of the CPU are sufficiently kind of uncoupled and modular. So that means that we can actually layer up our fetch, decode, execute cycle into a pipeline and triple our throughput. Of course, as we started to discover in that lecture last week, there are a variety of things that can go wrong when you have a pipeline like this. And one might be that if this is a conditional branch, if this instruction, like BEQ, label, then we can easily fetch this one, but we don't know what to fetch here. So that instruction is unknown. So 2, we don't know where that is. This is a location in memory, right? OX0001. This one, we don't know what its location in memory is because we don't know the outcome of the branch. So we only know that here at the end of there, we know the outcome. And then we know, oh, actually the branch failed. We just go on to the next location in memory, 2. So in that case, right, all this part of the pipeline would have to get pushed up. We'd end up with some bubbles, bubble, bubble, push up the fetch to here, and we would have lost our advantage. And there were some strategies that I discussed last week about putting bubbles in the pipeline. That's a strategy that saves us from crashing, but it wastes time. Maybe we could do some branch prediction. That'd be a very clever and wild way to do it. Maybe we could do out of order execution. If we had some way of reordering our instructions so that we can layer up as much as possible, maybe the sequencer can do that for us. They were pretty wild concepts, but pretty interesting. Then we had this multi-processing idea, right? Which bits of a CPU can we layer up, and which bits, and how can that help us? So here we have 3 different ideas. This one's multi-core, right? Multi-core. Because we just copy the whole CPU. That's great. That means we can simultaneously run multiple programs. We get the full performance of a full CPU for each one of those. Going backwards, there's this one where we're layering up all of this part, but not all of the working parts of the CPU, right? So the registers and flags and decoder sequencer are layered up, but the ALU and the memory connections are not. And what this means is that we can have 2 programs running on that CPU if we've just doubled it. And rather than our operating system having to do a context switch, which could take thousands of instructions to actually do, all the hardware has to do is flip around those register banks and flag banks and decoder sequencer, maybe even less than 1 instruction, and keep running with the other program, right? So we can keep doing this switch between those 2 banks and trick our CPU into allowing us to do, or trick our computer into allowing us to do multiple processes. They're not exactly simultaneous, but they can happen much more quickly than if we had to keep doing context switches. So this one's called hyperthreading. And And then finally, what if we didn't duplicate this stuff, but instead we duplicate our working part of our processor, our arithmetic logic units, times lots, right? Then we can do simultaneous instructions, well, SIMD, simultaneous instructions, multiple data. So if you've got a big array of numbers or a vector of numbers and you want to add it to another vector of numbers, if we only have one ALU, we just have to do them bit by bit by bit. But if we have some SIMD instructions that can access multiple ALUs, maybe we can take a chunk of those two arrays, give them these chunks to the ALU, and do it all in one instruction of each chunk. So we might make a big time saving in certain kinds of processing loads by having multiple execution units. And of course, the biggest version of this is GPUs, right? GPUs, and I showed you the slide of those like NVIDIA Volta architectures where there's loads of cores, and each core has loads of ALUs, like 64 ALUs. So it can do an instruction on 64 pixels or 64 numbers at once in each core, and just have really, really wide bandwidth in crunching through data with the same simple instructions. CPUs also have multi-core stuff, so they're basically like mega parallel processing machines. Yeah. Virtual memory. Don't think we had a slide about this one, but I talked about it a lot, right? So virtual memory is this idea where the operating system sits in between here. This is your actual memory map, and it actually gives each program an area of virtual memory to talk to, and then translates that into physical memory before independently of the CPU. So the operating system has defined a virtual memory unit to translate between addresses on bits on the board in the physical memory chips and this sort of logical virtual memory address. And whenever your CPU is saying to put things in this particular memory address, the virtual memory unit, memory management unit, says, oh, okay, well, I'm in this virtual memory mode, so that means I need to put it into this place in memory. So that memory management unit is responsible for mapping between physical memory and virtual memory, and it's a piece of hardware, so it has to be an additional component of your CPU. That's really not the OS, is it? It's the memory management unit. Memory management unit. That was a tricky question. Is virtual memory an architecture, hardware topic, or an OS software topic? Explain reasons for both points of view. I'll leave that question with you. Had a little bit of a look at these alternatives, right? The parallax propeller, which could work with multiple cores and not have interrupts. Showed you one of those. And then I showed you like this kind of alternative architecture. I don't know if you guys saw, but someone on Piazza was asking about another alternative architecture where they said, well, what if we have a toilet cistern which stores water, and that could store one bit of information, right? It's either full or empty. And then my mind started to wander to this kind of a bathroom CPU architecture where multiple toilets could be a register, and yeah, I don't know if that's an analogy we want to go too far down, but you can make computers out of anything. You can make them out of little levers. You can make them out of electrical kind of the mechanically electrical movable components like reed switches. And as we do, we can make them out of silicon chips. So there's lots of alternative ways that you can apply these same concepts. Of course, we tend to use the silicon ones, solid state, because they work, right? The mechanical ones, you could only have a very simple computer before you'd have inaccuracies in your mechanical assemblages, which would prevent the computer from working, which was kind of the reason why like that original Babbage difference engine from the 19th century never got off the ground because the tolerances in making gears to work in a certain way, once you have heaps of them, thousands in a mechanism, it wouldn't work. So your computations would be inaccurate at the end of the day, or fail to work, or jam up, or wear out in some other way. So it turns out that the best way we have of doing it right now is with silicon. Turing complete bathroom computer. Well, you've heard it here first, folks. Revise the bathroom computer concept, because there could be a question on it in the exam. Finally, we're done. That was an epic journey, everybody. I want to thank you for coming with me in COMP2300 this semester. I think it's been really challenging for everybody, and we've learned a lot about new ways of learning, new ways of communicating, new ways of teaching, and I hope that you've learned a lot about computing. Whenever I teach, I learn something about what I'm doing. I taught a lot of this topic last year, but I didn't teach the whole course. So this is the first time I've been able to teach this whole course from lecture 1, week 1 to week 12, and I had a really great time. I'm sure that you all have many stresses at the moment, dealing with your assignments, revising for the exam. We are here for you still on Piazza and until the exam, and in fact afterwards. And of course, you know, I would be very happy to hear from any of you who are interested in various kind of projects, or if you want to talk more about disco board stuff, or particularly about music technology, which is a particular interest of mine. So I hope that you've had a great time. I hope that you do a great assignment 3 response and have a great exam period. Make sure you do some revision across the whole course load. And I think I'm going to go to our ending slide because I'm running out of voice. So have a great exam period and a great holiday after that. I hope to see you around campus sometime soon, but you know, things are happening very slowly in terms of reopening. So look forward to the time when we can meet again.